guys, to another session of the Mind Grid. Today we're talking about fixed point binary representations and how we build complex math lookup tables using the fixed point tricks that we have learned in the previous videos. And as a quick reminder, if you have not seen those videos, go look up the fixed point series in my channel. And if you have not subscribed, then please go ahead and subscribe my channel. It really helps me. So with that, let's dive in. Before we show what the steps are, let's look at a quick cheat sheet and a recap of how things are done. What we are trying to do here is that we are trying to map fixed point to fixed point during our embedded or FPGA design process where we have a math function f of x and we are trying to map a fixed point input to a fixed point output without use of any library or any special IP, just simple lookup tables, right? So that's the trick here, fixed point to fixed point. Now, in order to convert this, what we will do is we'll take the help of Python offline, and what we will do is we will take the fixed point and we will first convert it or map it to floating point, just a number. Then we'll look up in Python, we'll compute using Python libraries or whatever functions, convert that to the output fx. And once we have the output fx, we will finally chop off the extra precision and convert it back into the fixed point, and that'll be our output. So in a sense, we will take um, our fixed point number, convert it in the middle to floating point, do the math on it, uh, and once the math is done, we'll convert it back to fixed point, and this process will give us our table. Now, in case you're not able to see, let me just erase this and um, draw this again here. So in a sense, we are taking fixed point. Our goal is to get a table of fixed point. In the middle, though, we'll convert it to floating point. We'll do the math on it. Math will give us floating point output. We'll convert that to fixed point, and then that is what we want to do here. Now, real quick, we'll use two main functions here. One is called toBinary, and the other is called toDecimal. Obviously, as the name suggests, toBinary will convert any decimal number into binary 2's complement. Um, and assuming this is the right size, obviously. And then if you're given a binary number, you can convert to a decimal value. This is obviously assuming this is an integer format. Um, so if it's given like that, the method to convert that is the following. Any number, bit 0 is 2 power 0, bit 1 is 2 power 1, and so on till the bit n minus 1, which is the last bit at the highest MSB. And that being the sign bit, what we do is it carries the weight of minus 2 to the power n minus 1, right? Keep that in mind that this minus is important because it's a sign bit, and that's how we do that. So this is basically a recap of what we have done in the previous videos. This is very easy to understand if you have followed those videos along. If you have not, please go ahead and watch those videos now before we dive into more details here. So now, how do we convert? So step by step, let's look at what we would do if we are asked to do this task that map this number that goes from -6 to +6. It's a sigmoid, which is a common function in neural networks or machine learning. And then this range on the y-axis is 0 to a 1. So that's what this is. Now, first thing first, it's a function that maps x to y, f of x. So we have to know what size the input is, what size the output is. In this case, we are saying it's 4.4 and this is 2.4. 4.4 because that can represent this -6 to +6. And the fractionals, hopefully, we just chose 4-bit fractionals. Hopefully that's enough. If not, then you can keep adding more to this and computing this. The output, we could have done 1.4 because there is not much going on here. There's not even a sign bit needed here. So basically, or you could just have the magnitude. But because we are having this magnitude, it could go to a +1, right? So +1 would need 2 bits for us. And so that's why we chose 2 bits here and 4 bits of fractionals, because we hope that that's enough. if that's not enough, he could always make this bigger, like 2.6 or 2.8, so on and so forth. So consider the input range. In our case, numbers going -6 to +6. Um, excuse me. So we can basically implement this as 1 sign bit, 3 magnitude bit, like we talked about, use 4 bits as fractionals, and that gives us 8-bit lookup table. So that is 8 bits of input, right? And as soon as you know this 8 bits, you know what the size of the um, number of rows in the table, because the 8 bits will go from 0 to 255, right? So 256 rows in this table. Next up, we look at how we construct the output. So for every 8-bit value, which is 0 to 255, we have to create a map here. So first we calculate its decimal value, like we said earlier, and it will map it to a floating point number, compute sigmoid and floating point, convert the sigmoid back into fixed point, and we know that the output precision is 2 plus 4, 6 bits, so we will easily convert that back to 2's complement, and that is the answer. So now let's dive into the code real quick. And what we're going to do here is that we using math just simply because we're trying to compute sigmoid, but it's pretty straightforward. It's 1 over 1 plus e to the power minus x. Matplotlib for plotting this. So now the main parameters are basically we have the input parameters and the output parameters, which is the fixed point sizes. The input fixed point is 4.4 format, the output is 2.4. So those are specified here. Total cases is basically because our input is 4 plus 4, the total number becomes 8-bit, and so total number of cases will be 256, which is what this is trying to compute. Next on, let me turn on the line numbers so you can refer to them. Um, so there are three main functions. The sigmoid is obviously there because we need to, that's our math function. And then keep in mind the two functions that we described in the cheat sheet, two binary and two decimal, basically are computed as such. You can go refer to that section of the slide deck earlier in the video. But as a recap, two binary will need to compute to positive and negative numbers, it needs to handle to 2's complement. And then from there to decimal, obviously given a binary number, you know how to convert to decimal, again described earlier. Finally, in the process of conversion, what we will do is we'll create three lists. The first list is just the x value, which is the real number of, the 0 to 55 converted to a real number. The y is going to be its value computed as sigmoid, and then the z would be its value. I guess z is the value that's computed as a sigmoid with full real number precision, and then y is the list that carries the number which has been reduced in precision based on our output format, which is 2.4. So just a for loop, and then we convert the for value into a number. The way we do this is first we take the whole number and convert that into decimal, and then we divide it by 2 to the power 4, and that gives us the real number. And then we take the sigmoid on it. Now, once we have the sigmoid, we have to now convert the output into a low precision number. The way you can do this is that the first thing you do is multiply that by the number of power fractionals, which is 2 to the power 4, and then you take an int on it. That chops off the extra precision. Then you divide again by 2 to the power 4 here, and that gives us the low precision fixed point number. And we don't care about orange here. And then finally you append them to the lists so that we can get a nice graph at the end. And once we come out of the for loop, we basically just plot it. So let's just run this, and now let's take a look at it. So what has happened in this graph is that the orange line is the real numbers, and real numbers obviously a high precision value. It is the floating point value. Now the blue line that you see is a stair step. You see this, so it loses precision a little bit, but not too much. So you can see that um, the blue line is a decent map of the orange line. And for the sake of our function, without losing that much um, accuracy, we have been able to map it from input to the output. Now, if you feel that this number of steps is like too coarse, then add more fractional bits to it, and this will get smaller and smaller, and it'll approach this as you add more and more bits. Like if you were to add, even 4 extra bits, it'll get closer and closer to this realistic um, or the highly accurate representation, and so you can minimize your error. But again, depending on how much you care about accuracy, you may not, depending on your application, it may be good enough for you to get by. So based on that, you can compute these values and tweak it so that you get higher precision based on your needs and your specifications. So the good thing that we have learned today, or the trick that we have learned today, is that we mapped fixed point numbers to fixed point output using a table approach. And this could map any math function that's coming from some library into just a lookup table. And once it's a lookup table, we have canned the algorithm into a lookup table. We don't need the math library anymore. And we can implement it in embedded code or in the FPGA or an ASIC without any math library. So that's it for today. Hopefully you enjoyed the video. If you did, give me a thumbs up, like and subscribe my channel.